Hello everyone, welcome to my presentation. In this presentation I will discuss our work towards image captioning. Here we try to implement scene graphs and use them to improve the image captioning. However, during our research we found some interesting results and we investigated further whether these scene graphs are actually good enough to improve image captioning. Alright, let's go ahead and jump in. So first of all, a short introduction about image captioning. So in image captioning, we want to, for a given image, create the most probable sentence that describes the content of this image. Now there are several methods and approaches that are being used and places where knowledge is gathered. So the two main places is directly transfer learning from a pre-trained convolutional neural network, where global knowledge so for the content of the image is transferred into the captioning process. Now a second method is to do first an object detection, and by doing this we have this set of boxes for objects in the image, as we can see in the lower figure here, and then for each of the boxes we have a feature, and using this we transfer knowledge from the actual objects in the image into the caption. And this has proven to be very useful and is the main technique still used. Now, how do we group this information from an image and from this set of objects? And we do that by using attention, and I assume most of you know what attention is, but in image captioning we do attention by having a set of regions in an image, and these can be global regions or they can be the object regions. And then while we process and generate the sentence, at each time step we do a soft selection over this set of regions to select the most important one. And as we can see here for our figure, when we want to predict the word bird, we clearly attend to only the pixels where the bird is present, to that region. So now the motivation for our process. So we know we have knowledge about the global scene and we have knowledge about the object in the image for generating the description. But what we are lacking is some knowledge regarding relations between objects and the interaction between them, because often it's not just a person sitting on person somewhere, he's doing something, but for instance sitting on a chair. And often there's also some action and movement. So I could be standing in a room or I could be walking down a hallway, and this should also be captured in the description. While the second one is very hard to capture with still images, the first one is actually possible by making use of scene graphs, where this kind of information is captured. So let's take a look at the scene graphs. So in a scene graph we have a set of nodes for objects in relations, and in this figure we indicate them with blue for the objects and orange for the relations. And so as we can see here in the far right image, we have an object for a horse and an object for a mountain. Now we know there is some relation between them. There's a structure is created where the relation behind is created, where we now can say the mountain is behind the horse. And this gives us more information about what is happening in the scene, and it gives us a better understanding. These scene graphs can also be automatically generated in a similar method as for the image captioning, as we can see here in the formula. So we want the most probable graph that describes the image here, and while in this caption we want a sentence, in the scene graph we want a set of nodes and relations. So what is our research goal? Well, we want to figure out if we can make use of this more advanced structure of the scene graph and use it to improve the captioning and the descriptions generated. Some work has already been done on this by Wang et al. And Lian Liang, who created both a model, the cascade model and the no more say less model. We will see that later on. But their results were a bit contradictory. So one of them had huge improvements, while the other was still a bit on par with the baselines with just using the object features. So we wanted to investigate this further if we can figure something out. Now next we wanted to see if find a measure on how to see what the quality of the scene graphs is and if this transfer learning might actually hurt the captioning. So to do our experiments, we created this model, and in our model there are two main pipelines. So we have the pipeline on the top, where a scene graph generation model is used to find a set of objects and relations. And for each of these objects and relations, a feature is generated, as we can see here in the green and blue boxes. Now in the bottom pipeline, we have the object detection algorithm that creates a set of objects and features for these objects. To use these features in our captioning model, we need some kind of mechanism that combines these. So we propose here several attention mechanisms. And the first one is flat attention, where we simply take the two set of features and concatenate these together, and we attend over them. A second method is to do a hierarchical attention. So first, for instance, we take an attention over the objects, the red boxes, and then by doing this, we find one important object feature, and then we can use this to take a selection over the scene graph features, to do a second selection there. And then these both are fed to the language generation model. And of course we can reverse this operation as well by first attending over the scene graph, followed by attending over the object. And as you can see in the top, we have this blurred out CGAT, and the CGAT is what we call the conditional graph attention network. It can also be a normal graph attention network. And since we have a scene graph, we could make use of some graph neural network to update these states further and get more knowledge of what is important, especially when we feed information from the captioning process into it. So how does this work? So for instance, when we have this graph here on the right, we want to update for one node in the network, we want to update the state. So in this case, men. So we look at all the neighboring nodes that are connected to men, and here we only look at the incoming ones, and we take the features from those and combine these into a feature that updates the state of the word men. So that men has knowledge about its neighbors directly encoded into it. So on the left is the traditional graph attention network, where the feature of the word man itself is used to do this update and decide how important each of the neighbor is. While we propose the conditional attention network, where an external feature decides how important each neighbor is. And in this case, our feature comes from the LSTM hidden state. This is then done for every node in the graph and in the scene graph to update all the nodes. So let's look at some results. So on the top of the line, we have the bottom-up, top-down baseline, which we re-implemented. And this is the baseline that doesn't make use of scene graphs. Then we have two models from Wang et al. And Li and Liang that make use of scene graphs in previous work, the cascade and the no more say less model. And then we have the set of our models, the flat attention and the hierarchical attention in different orders. As we look at these results, we get a very mixed set of numbers. And actually, we see that it's very hard across many of the metrics for the scene graph models to outperform the bottom-up, top-down baseline. While it's achieved in some of the models, it's with a very small margin, and in many of the other settings, it wasn't possible to improve the scores of the bottom-up, top-down model. So we wanted to investigate further if these features of the scene graphs are actually used. And to do this, we made use of the SPICE metric. And the SPICE metric is composed of multiple factors for which the F1 metric is computed. These are then combined in the overall score. We mainly look here at the objects and the relations score, since now we directly feed these using the scene graphs. So when we look at the results here, we actually see that except for one outlier, all of the models don't outperform the relation score with regards to the bottom-up top-down model. This was unexpected, since we know the difference between the bottom-up top-down and the scene graph models is that these relation features are used. However, we don't see this translated into the captions. So when we take a look at the quality of the scene graphs by computing the recall score for scene graphs, which is a commonly used metric here, and we plot these in order of the scores, we see this distribution. And what is surprising is that most of the scene graphs have a very low score, and this appears that it's very hard for the models to predict high quality scene graphs still. So the scene graph generation still needs some work to get these scores higher and have a consistent good scoring graph. Now, by splitting this set of images by using this metric, we have created a set of low scoring scene graphs, medium scoring scene graphs, and high scoring scene graphs, so we can do further analysis what the impact is of the quality of a scene graph. Now, when we look at the results here, we only show here for the average and the high scoring graphs. When we take a look at the full set of tables in the paper, the message gets a bit more nuanced, but to make the story a bit more simple, we showed these two tables which portray a clear message. So when we look in the table on the left, we have the average scoring graphs. And then we see the results that the bottom-up, top-down model for this set of images clearly outperforms across all the metrics. And however, when we then look to the high scoring graphs, although all the scores improve for all of the models, it clearly improves the most for the scene graph models, especially the hierarchical attention model, where it now has the top scoring results in all the metrics. This indicates that when the higher scoring scene graphs are used and we have a good quality scene graphs, we are able to make use of these features and we can actually improve the captions. This is clearly noted as well in the SPICE relation score, where for the bottom-up, top-down model this doesn't improve, but for all the scene graph models this improves by a large margin. Now let's summarize our results. So we have shown that in predicted scene graphs, there's still a lot of noise from the features and the predictions aren't perfect yet. And we also noted that this hurts the performance for the image captioning, and we cannot manage to get consistent results by using these scene graphs. However, when we only take a look at the high quality scene graphs, we noted in our experiments it's possible to get an improvement up to 3.3 CIDR scores. So this was our presentation, and thank you for listening.